again. Our second speaker is Oier Mees. He's a postdoc at UC Berkeley, working with Professor Sergio Levin. He received his PhD in computer science from the Freiburg University in 2023, supervised by Professor Dr. Wolfram Burger. And his research focuses on robot learning to enable robots to intelligently interact with both the physical world and humans and improve themselves over time. And these days, he's particularly interested in how he can build self-improving embodied foundation models that can generalize the same way that humans do. And his research has been nominated for several Best Paper awards, including ICRA and RAL. And previously, he also spent some time at NVIDIA, intern with Dieter Fox. With that, I'll give the screen to the speaker. And again, for questions, please use the Q&A feature.
Yeah, thank you so much. Can everybody hear me? Okay, perfect. Yeah, so thanks for the nice introduction. I'm very excited to present some of my work here in this talk called Embodied Multimodal Intelligence with Foundation Models, where I will mostly talk about research I've been done during my postdoc at UC Berkeley. So my research aims to develop generalist robot policies that unlock intelligent autonomy across diverse applications, such as home assistant robots, for example, that can work for and alongside humans. Concretely, this means developing novel solutions that generalize to essentially any robot in any scenario, even if the environment might be unstructured, as you can see from these videos that depict some results in the real world of my past works. And the canonical approach I'm taking towards this goal is inspired by advances in other areas like NLP and computer vision, where there has been this paradigm shift in which we have seen that essentially large models trained on diverse data sets typically surpass specialist models tailored for specific tasks like object detection, image captioning, or translation, for example. And so the workflow for developing these models, for example, in NLP, is that they train a large model on diverse data sets that can not only do a single task, but many, like code completion, question answering, translation, and so forth. And these will outperform, as aforementioned, models trained for a single task. Now, if we look at some of the most impactful advances in robot learning in the last years, we have seen that there's been really tremendous progress in performing dexterous tasks by methods like ACT and diffusion policies. However, these approaches are specialist policies that tend to work really well if you want to fit a model to a single task, but don't scale very well to learn more generalist, general purpose robot policies, as you would need to retrain these approaches for each and every new task that you want to learn in separate policies, right? And so the North Star of my research is to build a novel workflow for robotics by building generalist robot policies that can control not only one, but many robots in many environments and perform many tasks while working with and alongside humans. Therefore, ideally, I can envision a future in which you will be able to download your favorite robot brain online, and then out of the box, this robot could would start showing intelligent behavior in like a reasonable and useful manner for any type of robot that you might have. Okay, so I want to talk about what are the key ingredients that we need in order to develop these generalist robot policies, and what are some of the differences and challenges in applying the recipes that have worked really well in other areas like NLP to robotics. So let's start with the obvious one, which is that in robotics, we don't have the luxury of readily available large data sets that we can download and train on. Since robot data is typically scarce and expensive to collect, as we require usually like humans to teleoperate robots and so on. Additionally, robot data is highly multimodal and heterogeneous, as instead of training only on natural language, we have several sensing modalities that we need for our robots to interact with in the real world. and every robot will have different observation and action spaces. And also in robotics, we typically need high frequency control or even real-time control. So this means that we cannot really afford to wait, for a whole minute until the ChatGPT API returns an answer before we decide what our next action should be. And finally, as we develop models that can perform many tasks in many environments, we also need better ways of doing evaluations, because doing evaluations in robotics in the real world is really tedious and very expensive. So let's start by talking about the data. Where do we get this data from? Because no matter what the embodiment is, collecting data is very expensive, because we need to teleoperate the robot to collect data for each and every single task we want to learn. And I speak from experience here. As you can see me on the left, collecting some teleop data during my PhD in Germany. So this is why my research has focused on leveraging existing sources of data across existing embodiments. And if we look at the literature, there had been already some previous efforts to collect data sets for specific embodiments, but usually not in a format that allowed co-training on them, or like these data sets were not very compatible with each other, right? However, the key insight here is that essentially every robotics lab in the world typically needs to collect some sort of data to support their research, right? And this data, this would be like this polar dots here. This data might be like very niche and tailored to like the specific type of research that this labs will do, and small in quantity. So we don't typically think of uploading it to allow other people to use this data. So when I was wrapping up my PhD, I was able to collaborate with Google on this project called the OpenX Embodiment Dataset, where we essentially ask all our friends if they had existing robot data, so in different labs around the world, and we aggregated it into all these data sets into a common format that enabled training on all of them. And we ended up with over 1 million of real robot episodes, which was substantially more than any previous robot data set up to that date. And this contained a bunch of different robot embodiments, and it was like really a large-scale effort with over 34 research labs around the world that participated in this. Regarding the results, this was also the first time we saw some sparks of a single model trained on multiple robots across multiple datasets, surpassing the best previous method tailored for that particular setup. And personally, I was one of the 5 researchers and the only one in Europe that contributed continuous evaluations during the model development with the robot setup that I built during my PhD in Germany, which you can see on the top right. This paper has been quite impactful because it has really enabled algorithmic progress on the modeling side of generalist robot policies. And it will also serve as the foundation for most of the papers I will talk about in this talk. Okay, so far we have talked about where to get the data to train a generalist policy. But now even if we have a large diverse data set, how do we make use of this to train a model? How can we model this very diverse and heterogeneous data distribution? So maybe let's start with a basic example. So when we typically train a robot policy, right, the model will take as an input a current image observation and some task specification, which typically nowadays will be in the form of a natural language instruction, such as pick up the spoon in this case. And then the model will predict a series of actions like end effector poses that essentially should help the robot achieve that particular goal. And now our premise is that we want to fit our model on a large diverse data set of robot data sets, right? And if we squint a little bit and we replace this robot image observation with a kind of more regular internet image, and replace the task instruction with something like, let's say, caption the scene, then this starts to look very familiar. It starts to look very similar to a vision language model. And essentially, the key idea that the works that I will be presenting now build upon is that we can view robotics as a similar problem, where we are trying to learn a mapping from images and instructions to answers. Just that in our case, the answers are not text, but really robot actions. And so this means that if we formulate our problem as a multimodal sequence prediction problem, where we have language tokens, image tokens, and action tokens, then we can also leverage many of the advances made in multimodal sequence modeling from non-robotic domains to drive progress in robotics. So as a first step towards developing generalist policies, we developed Octo, an open source generalist policy, where we train a large transformer based on 800,000 robot trajectories of the OpenX embodiment dataset by tokenizing all these diverse heterogeneous inputs and action outputs. Now I think I have a problem because the sound will not play. I think the Zoom didn't allow me to click share sound. But what you're seeing here on this video, and what you would hear, is this is the first successful grasp of our Octo model that we developed at Berkeley at Google with the Google robot. So which we were serving via remote server, and you can see that we were like super excited to see how our model was doing the first successful grasps there. And so like before, I was doing the evals in Germany for Google, and now we kind of switched the roles. We asked them to do evals for the models we train at Berkeley. And it's also worth mentioning that this evals that we did were in a completely different building to the one Google had originally collected their data on. So, you know, it's also a good sign of generalization. Okay, so these were zero-shot evaluations. And I will not go too much into detail of the results. But one thing I really want to highlight for Octo is the adaptability aspect, because even if ideally even the model should be useful for your robot, even if we might not have pre-trained on it. Because it's possible that, you know, for your particular robot setup, you might have like a different amount of cameras, different action spaces, or maybe you want to do like joint control or something. So like ideally it still should be useful. So how can you adapt it? So if you have a new input, like let's say four-stroke readings, you can slot in a new input with a few tokens, and then you can fine-tune the model, and you really don't need to throw away the model weights from before. And because most of the parameters of Octo are inside the transformer, you get to retain most of the pre-trained knowledge. I won't go on detail about the fine-tuning results, but we found that the representations learned by Octo, or like essentially a robot foundation model, work much better than state-of-the-art visual representation learning methods like R3M or Visual Cortex 1 from Meta and so on. And in terms of impact, Octo has been quite popular by becoming one of the most uploaded robotic models on Hugging Face. And we have also seen researchers use it for fine-tuning around the world. So on the bottom left, you can see a video found on Twitter from a researcher that fine-tuned Octo on a Boston Dynamics spot robot with around 50 demonstrations, which is a completely unseen embodiment for the model. And more recently, on the bottom right, sorry, we found that a Japanese company is using Octo to drive their humanoid robot. So that's pretty exciting. Okay, so far I have showed how you can train a generalist policy on a diverse data set containing a bunch of single arm manipulation tasks. But how generalist is this really if all it can do is single arm manipulation? Because as you all know, robots come in many more morphologies. And this means that there is a lot more of existing robot data that we could be learning from, like self-driving cars, humanoids, quadrupeds, etc. Because there is this potential of transferring knowledge across all these different embodiments, right? So this is why my research has focused on developing a scalable approach that essentially can consume data from any robot embodiment. Concretely, we have added in this project more embodiments, such as by manual manipulation, navigation, or locomotion to the data mix that we originally trained Octo on for a total of 900,000 robot trajectories. And then again trained a large transformer with embodiment-specific heads on it. And we call this crossformer. So our crossformer model accepts variable observation inputs and predicts also variable action outputs, which we found that is pretty important in order to predict action chunks of different lengths to account for embodiment-specific control frequencies, because all these different embodiments, like they can do from 5 hertz to 50 hertz. So it's a really important design decision to account for that. And in order to maximize transfer across embodiments, we also try to maximize parameter sharing across embodiments. So all these design decisions lead essentially to a model that can consume data from any robot embodiment, because we also don't require to do any sort of action space alignment. And here are the rollouts from our model. And as you can see, we evaluated very challenging tasks like indoor and outdoor navigation, very dexterous tasks like by manual sushi cutting on the bottom left, or quadruped walking. And I want to highlight that all of these rollouts that you see come from the same model checkpoint. So we did not cherry pick like particular models for like a particular embodiment. So this is all the same set of neural network weights controlling all these different embodiments. And regarding quantitative results, we have found that our cross-embodied policy matches or outperforms specialist policies trained for specific embodiments, which is great because it's we are starting to see the same like success stories as people did in NLP. Crossformer has been quite impactful despite being a fairly recent paper, by receiving broad attention from media and also industry with several invited talks. But I think more importantly, we've seen that Crossformer has really enabled a spur in follow-up works in cross-embodied generalist policies, such as this work on the right from physical intelligence. So at this point in my talk, you might be wondering, okay, this sounds cool, and does this mean that scaling cross-embodied robot data is all we need? And I believe the answer is no, because even if we develop a robot capable of many tasks, this isn't going to be very useful if it cannot reason intelligently. So for the models I have shown so far, for instance, if the policy faces an out-of-distribution situation, they have no mechanism to intelligently solve it. And if we look, for example, what is happening with LLMs, so we see that even LLMs are typically trained on all of the internet, right? And even after seeing all this data and being trained on all of the internet, they're still not able to solve all the tasks we want them to be solving, right? And nowadays, this is why people are training LLMs specifically for reasoning, because reasoning are these compositional bits that can be reused and transferred to solve with existing knowledge, and we want to be doing the same for robotics. And because we are formulating now robotics as a multimodal sequence modeling problem, this means we can also try to transfer like these algorithmic advancements such as reasoning from LLMs. And so how do we do this? To this end, we recently released Embodied Chain of Thought, which is an approach where we try to make our models reason through the task at hand and the actions it's supposed to predict before actually predicting the action. So this means that instead of doing a direct mapping from images and language to action, as you can see in this video, we perform these embodied chain of thought reasoning steps before predicting the next actions to take. The idea is simple. Because we want to maximally use the robot data that we already have, we use internet scale foundation models to annotate our existing robot data by generating semantically grounded reasonings like subtasks, predicting bounding boxes of the objects to interact with next, or traces of how the gripper is going to move in the future, for instance. And now the core idea of embodied chain of thought is to train an autoregressive vision language action model. So this is a VLM fine-tuned to predict robot actions. That predicts this intermediate grounded reasoning steps before predicting robot actions. So essentially, this means that now we are forcing the model to think carefully and look carefully before acting. And these green blocks represent semantic reasoning steps that are happening in a language space, similar to what LLMs do. And the purple ones are the visual reasoning steps that are essentially grounded in the image space, like predicting traces of the gripper, bounding boxes of the objects to interact with, next, and so forth. And we evaluated this model on really challenging out-of-distribution tasks like spatial relations, unseen tasks and objects, and found that this resulted in a 30% performance boost over the same model, OpenVLA in this case, without the reasoning. And we even surpass state-of-the-art closed source model RT2X from Google, which has 55 billion parameters, much larger than our model that has just 7. And finally, not only does embodied chain of thought improve performance, but it also makes robot policies more interpretable, because now you can see what the model is thinking of doing before it actually does it. And it also makes it more interactive because it allows humans to correct behaviors by editing these reasoning chains online. And this has been also very impactful work by becoming the new standard to train VLAs with reasoning, as it leverages better the VLM pre-training, and it also has seen quite widespread adoption by industry and academia. Okay, so far I have talked about the data and the modeling side of generalist robot policies. And last but not least, I want to really talk briefly about evaluation, because this is kind of a very difficult problem in robotics in general, because evaluating real-world policies is really expensive, because it just takes a really long time, and people might bump into grippers or cameras. Sorry, grippers might get stuck, and it just takes like a really long time, right? So and in our case, because we have generalist robot policies, like the cost of doing evals for all these possible tasks that they can do in all these different embodiments, it's just like a tremendous cost. So one way to get around this problem is to use simulation, as this makes research more accessible to people who don't have the same robot as you, but also it makes the numbers more reproducible in general. So this is why during my PhD, I developed Calvin, which was kind of the first public benchmark for generalist policies, where a single agent must solve complex manipulation tasks by understanding a series of language expressions in a row and generalize to unseen environments. I will not go into the details of the benchmark, but it's been a very popular benchmark that's been very well received by both the vision and the robotics communities, as it has allowed really to drive like algorithmic development. And it's been like so popular that even I think one of the coolest things I've seen is that this lab at TU Munich, they decided to build a real world replica of the sim benchmark to do sim to real experiments with it. So that's really cool. And so Calvin is very useful if you can like train and test on simulated data, but we are actually interested in deploying our models in the real world, right? Unlike most of our generalist policies will typically be trained on real world data. So what do we do about that, right? Like we haven't really solved the problem. And we saw this in a painful way with Octo. Like for Octo, we had like a large number of collaborators that did evaluations for us across different institutions. But you cannot ask them like every few days to do like new evals for you. So this is why we started a parallel project, which we coined Simpler. This was a collaboration with UC San Diego, Stanford, Berkeley, and Google, that tries to leverage sim evals for policies trained on real world data. the hope is that if we can find a way to evaluate our real-world policies in simulation in a way that informs us about how they would perform in the real world, well, then we can just sit back and enjoy life while we let the simulator run a large number of evals. And this also has the advantage of making the evaluations more reproducible. I will not go into the details of exactly how this approach works, but it has really become a crucial ingredient in our lab and in many other labs to develop and test new generalist policies. So really becoming a daily driver and democratizing research for people who don't have the same robot setups. And maybe it has become even maybe too popular because we have seen that people are writing entire analysis papers of VLAs by just doing thousands and thousands of rollouts in sim, but no other additional real-world robot experiments, which maybe they should try to do some. And yeah, that's all I have. So to recap, I talked about what are the key ingredients to develop generalist robot policies. I talked about how to use existing robot data from diverse heterogeneous data sets in order to train cross-embodied policies that can control a wide variety of robot morphologies. And I also talked about how we can endow these models with intelligent reasoning abilities that allows them to generalize better to out-of-distribution situation. And I also briefly talked about how we can use real to sim evaluation frameworks to democratize research around generalist policies. And for the future, I'm very motivated by developing intelligent assistant robots that can perform tasks for and alongside humans in unstructured environments for extended periods of time. And I think the 4 key ingredients that we need towards achieving this goal are advances in dexterous mobile manipulation, intelligent embodied reasoning, lifelong learning, and rapid adaptation. With this, I want to finish by thanking my fantastic collaborators, without whom much of this research would have not been possible. And yeah, thank you for your attention. I'm happy to answer any questions you might have.
Great, thank you very much. Very interesting talk. We have time for a couple of questions. So if you have questions, please put them on the Q&A feature. I'll start with the first one that we already have. So you probably talked about this, but what if the training for Octo is biased towards scene image sensing, but my robot only has depth sensors and LiDAR?
Yes. I think for depth sensing and LiDAR, so you would need to see how you would need to essentially add another encoder to process your new modalities. You would have to see if there is any pre-trained encoders that are specific to your modality that you can use, and then tokenize this and add it into the Octo fine-tuning. Yeah.
And then second question, are you doing any fine-tuning for COT reasoning or just using FMs and API calls?
Fine-tuning for chain of thought reasoning. No, so I'm not sure I understand 100% this question, but for the embodied chain of thought paper, we used existing foundation models from other areas like SAM, Gemini, and so on to generate this synthetic reasonings for the offline robot data that we already have. So essentially, you can see this as some sort of distillation of existing foundation models from other areas into your one robot policy.
And then one last question, would it be possible to incorporate robot-specific constraints in this framework so the action sequence is safe and executable by the robot?
Yeah, I think there are 2 things. I think for embodied chain of thought, it would be very interesting to see if you could leverage this framework to reason about safety in the future. So let's say you have a self-driving car or something, You know, like if you're already kind of reasoning about how objects are moving, or in this case, like traffic participants are moving, trying to maybe predict like, you know, like safety related reasonings before executing the actions or predicting the actions. I think that would be super cool. If you're asking about like low level safety, like for like robot manipulation and stuff, we typically rely on, you know, like the low level controller, and you know, like we have some constraints on the workspace that we use to ensure that you know, you're not executing unsafe actions, right? So for example, if you use like delta end effector control, then you will typically like also clip, for example, like how large of a displacement you allow your policy to do like in at every step.
All right, thank you so much. I think that marks the end of our time slot. So I would like to thank both of our speakers again, and then we'll have 2 additional talks next week for our future leaders seminar series. Thank you very much.